Hello, and welcome to Space for Sleep. There is a number so familiar that it can seem almost ordinary. 299,792,458 meters per second. It is usually introduced as the speed of light, a cosmic maximum, the fastest anything can travel, a boundary placed across the universe like an invisible sign. But that description, while true, is incomplete. The number does not belong to light in the way the speed of sound belongs to air, or the speed of a wave belongs to water. It is not merely the pace at which one particular thing happens to move. It is woven into the way distance and duration fit together. It marks the boundary between events that can influence one another and events that cannot. It connects mass with energy, shapes the view from a fast-moving spacecraft, determines how clocks disagree, and tells us what portion of the universe can ever be seen. Even the number itself has changed its role. For centuries, scientists try to measure it. Today, in the International System of Units, its numerical value is fixed exactly. The meter is defined through the distance light travels in vacuum during a specified fraction of a second. We no longer use a meter to discover the speed of light. We use the speed of light to define the meter. That reversal is a clue. The speed of light is not simply one measured property among many. It has become part of the framework by which measurement itself is organized. Yet the deeper surprise is still ahead. Imagine standing beside a railway track while a train passes at tremendous speed. A lamp at the front of the train flashes. The light moves through the carriage and out into the night. Common sense suggests that someone on the train and someone standing beside the track should disagree about the light's speed. The passenger should measure one value relative to the moving train. The observer on the ground should add or subtract the train's speed. That is how ordinary velocities work. A ball thrown forward from a moving vehicle is faster relative to the road than relative to the person who threw it. Sound travels at a definite speed relative to air, and wind changes how quickly it reaches different observers. Ocean waves move relative to water. Every familiar example teaches the same lesson. Light refuses to follow it. Every inertial observer who measures light moving through vacuum obtains the same value, regardless of how the source moves and regardless of how the observer moves. The train can chase the beam. It can race away from it. It can move at 99% of the speed of light. The passenger still measures the departing light at the same value as the observer beside the track. This is not because measuring instruments become confused. Space and time adjust. Clocks disagree. Distances disagree. Simultaneity becomes relative. The universe preserves the same light speed by allowing observers to disagree about almost everything used to calculate a speed. The speed remains fixed because space and time do not. That is what the phrase cosmic speed limit hides. It sounds as though the universe contains ordinary space and ordinary time, then adds one rule saying that nothing may move too quickly. The actual structure is stranger. The invariant speed is built into spacetime first. The limit follows from that structure. To understand how such an idea became necessary, it helps to begin in an age when no one knew whether light had any travel time at all. A lantern is uncovered on a distant hill. The flash appears immediate. No human sense can detect the delay. Light crosses a room before a nervous system can begin to respond. It crosses a city in a tiny fraction of a blink. For ancient philosophers, instantaneous transmission was therefore a reasonable possibility. Some thinkers argued that vision worked through rays sent outward by the eyes. Others imagined light filling space at once. The question remained difficult because any terrestrial distance seemed too small and any available clock too slow. Galileo attempted a direct test in the 17th century. He proposed placing observers with covered lanterns on separated hills. One observer would reveal a light. The other would reveal a second lantern as soon as the first became visible. Any additional delay might show that light required time to cross the distance. The experiment could not succeed with human reactions and distances of a few kilometers. Light travels 1 kilometer in a little more than 3/millionths of a second. The delay caused by brains, eyes, hands, and shutters is enormously larger. Galileo did not prove that light was instantaneous. He concluded that if its speed was finite, it was extremely great. The first convincing evidence came from a clock in the sky. Jupiter's moon Io repeatedly disappears into the giant planet's shadow. These eclipses can be predicted. In the 17th century, they were studied partly because their regular timing promised a celestial method for determining longitude. Ole Romer noticed that the eclipses did not arrive exactly when a simple schedule expected. When Earth moved toward Jupiter, the events appeared progressively early. When Earth moved away, they appeared progressively late. Io was not changing its orbital rhythm to follow Earth. The changing delay belonged to the light. As Earth traveled to the far side of its orbit, the distance from Jupiter increased by roughly the diameter of Earth's orbit. Light needed additional time to cross that distance. Romer used the pattern to argue in 1676 that light travels at a finite speed and even predicted that an upcoming eclipse would appear later than expected. The prediction succeeded. The first numerical estimate associated with the method was still imprecise. The size of Earth's orbit was not known accurately enough, and the timing data were limited. Christian Huygens used Romer's result to calculate a value lower than the modern one, but unmistakably finite and astonishingly fast. For the first time, light had a travel time that could be seen across the solar system. A moon disappearing behind Jupiter had become a cosmic stopwatch. The measurement also introduced a truth that now shapes astronomy. Looking across space means looking into the past. Jupiter is seen as it was tens of minutes ago, depending on the planet's positions. The Sun is seen as it was a little more than 8 minutes ago. The nearest star beyond the Sun is seen more than 4 years in the past. The Andromeda Galaxy appears as it was about 2.5 million years ago. Astronomy never sees a distant object exactly as it is now. There is no universal image of the present waiting to be photographed. Every observation arrives along a path, and the path requires time. During the 18th and 19th centuries, measurements improved. James Bradley used the aberration of starlight, an apparent shift caused by Earth's orbital motion combined with the finite travel speed of light. Hippolyte Fizeau sent light through gaps in a rotating toothed wheel toward a distant mirror. At a particular rotation rate, returning light met a tooth instead of the opening through which it had departed. The wheel turned during the light's journey, allowing the travel time to be inferred. Léon Foucault replaced the toothed wheel with a rotating mirror and achieved greater precision. Albert Michelson later refined rotating mirror methods across long measured paths. These experiments transformed a delay once visible only across the orbit of Earth into something measurable in a laboratory. But the growing precision created a deeper problem. What was light moving through? Water waves require water. Sound requires a material medium such as gas, liquid, or solid. A wave seems to be a pattern traveling through something. 19th century physics therefore assumed that light must move through a universal substance called the luminiferous ether. The ether had to possess extraordinary properties. It had to fill empty space, pass through matter, carry transverse waves, and remain nearly undetectable. It could not slow planets through drag. It needed enough rigidity to support rapid waves while offering almost no resistance to ordinary objects. The idea became even more important after James Clerk Maxwell unified electricity and magnetism. Electric fields can produce magnetic effects. Changing magnetic fields can produce electric effects. Maxwell's equations showed that a changing electric field and a changing magnetic field could sustain one another and propagate as a wave. When the predicted propagation speed was calculated from electromagnetic quantities measured in the laboratory, it matched the known speed of light. Light was electromagnetic radiation. Visible colors were one narrow portion of a much wider family. Radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays all belong to the same electromagnetic field. Their wavelengths and frequencies differed. Their vacuum propagation speed did not. This was one of the great unifications in science. It also made the ether problem unavoidable. Maxwell's theory seemed to identify a definite wave speed, but a speed must be measured relative to something. Sound speed is measured relative to the air. A boat's speed is measured relative to water or shore. If electromagnetic waves crossed an ether, then their speed should be fixed relative to the ether. Earth moves around the sun. The solar system moves through the galaxy. Unless Earth happened to be perfectly at rest in the ether, the planet should experience an ether wind. Light sent along Earth's motion should behave differently from light sent across it. Albert Michelson and Edward Morley built an interferometer to search for this difference. A beam was split into perpendicular paths, reflected, and recombined. If one path lay more directly along Earth's motion through the ether, the travel times should differ slightly. The recombined waves would shift their interference pattern as the apparatus rotated or as Earth's orbital direction changed. The expected effect was small, but within the design's purpose. The decisive ether wind did not appear. The result did not immediately produce special relativity. Scientists explored alternatives. Perhaps moving objects contracted in the direction of motion. Perhaps clocks and electromagnetic forces adjusted. Hendrik Lorentz and George Fitzgerald developed mathematical ideas that could preserve Maxwell's equations while explaining the failed ether detection. The equations began to point toward a new structure before their meaning was fully understood. Then, in 1905, Albert Einstein removed the hidden stage on which the old picture depended. There was no need to identify a privileged state of absolute rest. The laws of physics could take the same form for every inertial observer, and light and vacuum could have the same measured speed for each of them, independent of the source. Einstein did not begin by asking how matter physically shrinks while moving through an ether. He asked what space and time must mean if the relativity principle and the invariant light speed are both true. The answer began with clocks. Not one universal clock, but many clocks moving relative to one another. Suppose two lightning flashes strike the ends of a long platform. An observer standing exactly halfway between the strikes receives both flashes together and declares the events simultaneous. Now imagine an observer on a train moving toward one flash and away from the other. That observer meets the forward flash sooner and the rear flash later. Could the difference be blamed on light traveling at different speeds relative to the moving train? Special relativity says no. The train observer also measures each light signal locally at the same invariant speed. The difference must therefore lie in the timing of the strikes. Events simultaneous for the platform observer are not simultaneous for the train observer. This is not a delay in human perception. It is not merely that information arrives late. After travel times are properly accounted for, different inertial observers can still disagree about which distant events occurred at the same time. There is no universal present spread across all of space. The speed of light forces each observer to build a definition of distant simultaneity using signals and clocks. Different states of motion produce different slices through space-time. That is the first great transformation hidden inside the number. A finite speed alone would create delays. An invariant speed changes the meaning of now. A simple imaginary clock reveals how deeply the change reaches. Picture two mirrors facing one another, one above the other, with a pulse of light bouncing between them. Each round trip is one tick. To an observer traveling beside the clock, the pulse moves straight upward and downward. The distance between the mirrors and the speed of light determine the ticking rate. Now watch the same clock pass from left to right. During the time the light travels toward the upper mirror, the entire apparatus moves sideways. The pulse therefore follows a diagonal path relative to the stationary observer. It follows another diagonal on the return journey. The moving light travels farther between ticks. Yet both observers must measure the light at the same speed. If the path is longer and the speed is unchanged, the tick must take more time. The moving clock runs slowly. Every process inside the moving clock slows by the same factor. If only one mechanism changed, the observer inside could detect motion relative to an absolute background. But all local processes obey the same laws. Atomic transitions, electrical signals, chemical reactions, biological aging, and the motion of mechanical parts all share the change. The traveler feels normal. 1 second on the spacecraft remains 1 second for the crew. Their hearts do not seem delayed. Their thoughts do not stretch. Their rulers do not shrink in their own frame. It is the comparison between different paths through space-time that produces the disagreement. This effect is called time dilation, but the phrase can suggest that time is a substance being squeezed. A better picture is that elapsed time depends on the route between events. Two clocks can begin together, follow different motions, and reunite with different readings. Neither malfunctioned. Each recorded the proper time along its own path. This is not confined to imaginary spacecraft. Unstable particles created high in Earth's atmosphere provide a natural demonstration. Cosmic rays strike atomic nuclei and produce particles called muons. A muon at rest survives, on average, only a little more than 2 millionths of a second before decaying. Even traveling near light speed, such a short lifetime would seem insufficient for many muons to cross the atmosphere and reach the ground. Yet they do. From Earth's frame, the moving muon's internal clock runs slowly, allowing it to travel farther before decay. From the muon's frame, the atmosphere is length contracted, so the ground is closer. Both descriptions predict the same detection. Particle accelerators confirm the effect with extraordinary precision. Fast particles survive longer, decay differently in laboratory time, and carry energy according to relativistic equations. Special relativity is not an idea reserved for distant stars. It operates inside every accelerator beam and every satellite navigation system. Length contraction accompanies time dilation. A rod moving relative to an observer is measured to be shorter along the direction of motion. This is sometimes described as an optical illusion, but ordinary visual appearance is more complicated. Light from different parts of a fast object reaches the eye at different times, creating distortions that can resemble rotation. Length contraction is a statement about measurement. To measure the ends of a moving rod, an observer must record their positions at the same time in that observer's frame. Because simultaneity differs between frames, the measured length differs as well. Time dilation, length contraction, and relativity of simultaneity are not three unrelated corrections. They are one geometry viewed from different angles. The equations that connect inertial observers are called Lorentz transformations. At ordinary speeds, they reduce almost perfectly to the familiar rules of Galileo. A walking person on a train adds their speed to the train's speed, and the tiny relativistic correction is undetectable. Near the invariant speed, the old addition rule fails. If a spacecraft moves at a large fraction of light speed and launches another craft forward, an observer does not simply add the two velocities in the classical way. The relativistic rule combines them so that the result remains below the invariant limit. No sequence of ordinary boosts carries a massive object through the boundary. This is often introduced as a trick performed by nature to protect the speed of light. But the Lorentz transformation is not an emergency adjustment. It is the consistent way observers relate space and time when the invariant speed exists. The geometry can be drawn. Place time vertically and one direction of space horizontally. An event is a point. A moving object traces a line called a world line. A flash emitted from one event travels outward at the invariant speed, creating the sides of a light cone. Events inside the future light cone can be influenced by the original event using signals moving at or below the limit. Events inside the past light cone could have influenced it. Events outside the cone are too far away in space for any allowed signal to connect them in the available time. The cone is not made of light. Light traces its boundary because light is massless. Any other massless disturbance also follows the same local causal boundary. Gravitational waves propagate along it in general relativity. The deeper object is the causal structure of spacetime. This is why physicists often use the letter C even in discussions where no lamp, photon, or electromagnetic field appears. The constant C is the invariant speed. Light travels at it in vacuum because photons have zero rest mass. The speed limit is not derived from a special rule imposed on glowing objects. It belongs to the geometry, and light reveals it. Suppose the sun vanished in an impossible instant. Earth would not immediately leave its orbit, and darkness would not arrive immediately. Changes in the gravitational field and changes in the electromagnetic field would reach Earth after a little more than 8 minutes. Until then, the planet's local environment would remain causally connected to the earlier sun. General relativity does not permit gravity to update everywhere at once. Disturbances in spacetime propagate at the invariant speed. This was tested dramatically when two neutron stars merged in a distant galaxy. Gravitational waves arrived first, followed less than 2 seconds later by gamma rays. The signals had traveled for roughly 130 million years. The small delay could arise in the source, because light and gravitational waves need not be emitted at precisely the same moment. The observation constrained any difference between their propagation speeds to an extraordinarily tiny fraction. A constant once discovered through light now links electromagnetism, gravity, and causality. The light cone also explains why faster-than-light communication would create more than a race. It would threaten the ordering of cause and effect. Two events outside one another's light cones are called space-like separated. Different inertial observers can disagree about which happened first. This does not create a contradiction because neither can cause the other using signals restricted to the light cone. If a controllable signal could cross the space-like gap, one observer might describe it as traveling forward in time, while another describes it as arriving before it was sent. With a second appropriately moving transmitter, messages could be arranged into a loop that returns information to its own past. A warning could arrive before the decision to send it. The problem is not merely that faster travel sounds difficult. The causal order of spacetime is built around the invariant speed. Crossing the boundary means entering regions where temporal order depends on the observer. This is why the phrase speed of causality is more revealing than speed of light. It tells us which events can be connected by influence. It also divides the universe into what is reachable, what is observable, and what remains outside every possible exchange. The boundary applies locally. That word becomes important in curved and expanding spacetime. Near Earth, a freely falling observer in a sufficiently small region measures light in vacuum at exactly c. Near a black hole, a freely falling observer also measures passing light locally at c. No local experiment finds light slowing as it crosses an event horizon. A distant coordinate system may assign a different coordinate speed. Light approaching a horizon can appear increasingly delayed and redshifted to a distant observer. Radar signals passing near a massive body experience a Shapiro time delay. Cosmological distances expand while light travels. None of these effects means the local invariant speed has changed. Coordinates are labels. In curved spacetime, distant comparisons depend on how those labels are chosen. The local causal structure remains light-like. This distinction prevents several common misunderstandings. Light does not struggle through gravity because gravity pulls against its engine. A photon always follows the straightest available path through curved spacetime, called a null geodesic. What appears as bending is the geometry of the path itself. Near the Sun, starlight follows curved spacetime and changes apparent direction. Around a black hole, some light paths orbit temporarily near a photon region. In the simplest classical description of a non-rotating black hole, all future directed paths inside the event horizon lead towards smaller radius, including the paths followed by light. The horizon is not a place where light locally becomes stationary. It is a boundary in causal structure. Beyond it, moving inward is as unavoidable as moving toward the future. The same constant defines the tilt of every local light cone. Matter remains inside. Light follows the surface. The shape and orientation of the cones change with gravity, but the local boundary does not lose its meaning. This geometric view also clarifies why a massive object cannot be accelerated to see. A massive particle traces a time-like world line inside the light cone. A photon traces a null world line on the cone. These are different classes of path. No ordinary acceleration smoothly changes a time-like path into a null one using finite energy. The familiar explanation says that the energy required rises without limit. That is correct, but the geometry comes first. As the object's speed approaches c relative to an inertial frame, the Lorentz factor grows. Additional energy produces smaller and smaller increases in speed, while momentum and energy continue rising. At 90% of c, there is still room to accelerate. At 99%, the next equal increase in energy buys less speed. At 99.9%, less again. The limit is approached but never reached by a massive object. This does not mean the object's mass itself must be described as increasing. Older textbooks often use the term relativistic mass. Modern physics usually keeps mass invariant and says that energy and momentum increase. The object's resistance to acceleration changes, but its rest mass remains the same. The complete relationship between energy, momentum, and rest mass is broader than the famous equation found on posters. The square of the total energy equals the square of momentum multiplied by the square of c, plus the square of the rest mass multiplied by the fourth power of c. For an object at rest, momentum is 0, leaving the rest energy E equals mc squared. For a photon, rest mass is 0, leaving energy equal to momentum times c. The full relation shows massive and massless particles as different cases within one structure. A massive particle can have a rest frame. There is an inertial frame in which its spatial momentum is 0. A photon cannot. No observer can accelerate into a frame where light in vacuum stands still. The Lorentz transformation required to reach that frame becomes singular at c. There is no clock traveling beside a photon, no ruler held at rest with it, and no valid inertial perspective from which the universe can be described. This makes a popular phrase misleading. It is often said that from a photon's point of view, no time passes and the entire journey is instantaneous. The mathematical interval along a light-like path is indeed 0 proper time. But a photon does not possess a rest frame or a point of view in special relativity. Proper time is what a clock measures along a time-like path. No possible clock follows a light-like world line while remaining at rest with a photon. We can say that the space-time interval between emission and absorption is light-like. We should not turn that statement into the experience of an imaginary observer who cannot exist. The difference matters because the most interesting facts about C are already strange enough without adding an undefined perspective. A beam from a distant galaxy may travel for billions of years according to cosmological clocks. Its path contains zero proper time in the geometric sense used for null intervals. Those statements do not conflict because they answer different questions. One concerns elapsed time measured by physical observers and clocks. The other concerns the invariant classification of a path. The universe does not provide one master duration attached to every journey. It provides relationships among events, world lines, and measurements. The invariant speed is the thread holding those relationships together. The phrase speed of light becomes more complicated as soon as light enters matter. In vacuum, C has a precise role. In glass, water, air, ice, plasma, and other materials, a pulse of light can advance more slowly. The difference produces refraction, lenses, rainbows, optical fibers, and the blue glow around nuclear reactors. This sounds like a contradiction. If every local observer measures light at c, how can light move through glass at a smaller speed? The answer begins by separating vacuum propagation from the collective behavior of light and matter. A transparent material contains charged particles, especially electrons bound within atoms and molecules. The electromagnetic field of an incoming wave drives those charges. They respond, oscillate, and produce their own electromagnetic fields. The original field and the induced response combine. The resulting wave inside the material has a different phase relationship and a different propagation speed from a wave in vacuum. It is tempting to describe this as photons repeatedly crashing into atoms, being absorbed, waiting, and then being re-emitted. That picture can be useful in some situations involving real absorption and fluorescence, but it is not the general explanation of ordinary transparent refraction. In a clear window, the transmitted field is usually a coherent response of the material. The atoms do not simply erase each photon and release an unrelated replacement after a random pause. The wave and the medium form a coupled system. Different notions of speed then appear. The phase velocity describes how a crest of a perfectly repeating wave pattern moves. The group velocity describes how the envelope of a pulse, and often its energy, moves through a medium. The front velocity concerns the first possible arrival of a genuinely new disturbance. In simple transparent materials, these speeds behave in familiar ways. The group velocity is below c, and a pulse arrives later than it would through vacuum. In strongly dispersive media, where the response changes rapidly with frequency, phase or group velocities can take surprising values. A group velocity can exceed c, become negative, or appear to send a pulse peak out before the peak would have arrived through vacuum. This does not permit information to outrun causality. A smooth pulse already has a leading tail. The medium reshapes and amplifies different parts of the waveform, moving the location of the maximum. The peak is not a permanently labeled object. It can be reconstructed from earlier portions of the signal. The arrival of a truly new feature remains limited by the causal front. The distinction is subtle because everyday language treats a pulse as a little package with a single speed. In reality, a waveform contains many frequencies. A material delays each frequency differently. The combined shape can evolve while traveling. This is how experiments can report slow light, stopped light, or apparently superluminal group velocities without changing the invariant structure of spacetime. In famous slow light experiments, a carefully prepared atomic gas becomes extremely dispersive within a narrow frequency range. A light pulse entering the gas can have a group velocity reduced to walking speed or below. The pulse is not simply a tiny luminous object crawling between stationary atoms. Part of the excitation is stored coherently in the atomic medium. The traveling electromagnetic field and the collective atomic state exchange energy and information. When light is said to be stopped, the optical information is mapped into a material excitation and later converted back into a departing pulse. The experiment is extraordinary but c has not been lowered. Vacuum light still defines the causal limit. The medium has created a coupled process with a long delay. A simpler example occurs in water. The refractive index of water for visible light is about 1.33, varying with wavelength. The phase velocity is therefore roughly 3/4 of c. Different colors slow by different amounts, which is why a prism separates white light and why water droplets form rainbows. Blue light and red light experience slightly different refractive indices. At the boundary between air and glass or water, the change in speed and wavelength bends the ray according to the geometry of wavefronts. The frequency remains continuous across the boundary. The wavelength changes. A transparent material therefore reveals that the common phrase light travels at c requires an unstated condition. Light in vacuum travels at c locally. Light propagating as a coupled excitation through matter may have a lower effective speed. This allows a charged particle to move faster than light in that material while remaining slower than c. When an energetic electron passes through water, it disturbs molecules along its path. If the electron moves more slowly than the relevant light speed in the medium, the emitted disturbances spread without forming a coherent shock front. If it moves faster, the electromagnetic disturbances overlap along a cone, like pressure waves forming a sonic boom behind a supersonic aircraft. The result is Cherenkov radiation. Its characteristic blue glow surrounds the cores of some nuclear reactors because fast-charged particles move through water faster than light's phase velocity in water. The particles do not violate relativity. They remain below c in vacuum. The cone angle carries information about the particle's speed. Cherenkov detectors are used in particle physics, neutrino astronomy, and cosmic ray experiments. Vast tanks of purified water wait in darkness for faint cones of light produced when a rare particle interaction launches a fast charged particle. The speed of light in matter becomes an instrument for detecting almost invisible events. Nature supplies another apparent exception in astronomy. Jets from active galaxies can seem to move across the sky faster than light. A bright knot in a jet may be traveling close to c at a small angle toward Earth. Because it moves toward us while emitting successive light signals, the later signal has less distance to travel. The separation between arrival times becomes compressed. When the transverse motion is divided by that shortened interval, the apparent speed across the sky can exceed c. Nothing locally outruns light. Geometry and light travel delay create superluminal appearance. A similar caution applies when a laser spot sweeps across a distant surface. Rotate a laser quickly enough, and the illuminated point on the moon could move across the lunar ground faster than c. But the spot is not one object carrying matter or information from one location to the next. Each point on the moon is illuminated by a different photon launched from Earth. No signal travels sideways along the surface at the spot's apparent speed. A shadow can also sweep faster than light. So can the intersection point of two moving lines. Patterns are not automatically causal messengers. The invariant limit applies to local transfer of matter, energy, and usable information. This distinction becomes even more important in quantum physics. Entangled particles can display correlations that no local hidden variable model can explain. Measurements made far apart are connected in a way that appears immediate in the mathematical description. Yet entanglement cannot be used to send a controllable message faster than light. Each observer sees outcomes that are locally unpredictable. The correlation becomes visible only when ordinary information from the two locations is later compared through a causal channel. Quantum theory violates classical expectations about separability. It does not provide a faster-than-light telephone. Quantum tunneling creates another source of misleading speeds. A wave packet encountering a barrier can produce a transmitted peak whose timing suggests that the crossing happened faster than light would traverse the same distance. but the transmitted pulse is reshaped, and the relevant causal information does not propagate beyond the light cone. The earliest front remains constrained. The same principle survives through many apparent loopholes. Phase velocity can exceed c. A group peak can behave strangely. A spot can sweep faster. A distant jet can look superluminal. Entanglement can produce non-classical correlations. Space itself can expand so that distant galaxies separate faster than c. None of these allows a local message to be sent through space-time outside the causal cone. The last example, cosmic expansion, deserves special care. The statement that nothing moves faster than light is often interpreted as saying that the distance between any two objects can never increase faster than c. General relativity does not impose that rule on sufficiently distant objects in an expanding universe. Galaxies carried apart by cosmic expansion can have recession rates greater than c when distance is defined in a standard cosmological way. They are not locally racing through space past neighboring observers at superluminal speed. The space between distant regions is expanding. Locally, each galaxy remains nearly at rest with nearby cosmic matter, and every nearby observer measures passing light at c. Over enormous distances, adding the expansion of many intervening regions can produce a rate of separation above c. Some galaxies we observe today have always been receding from us faster than light according to certain distance definitions. Yet their ancient light can still reach us because the expansion rate changed and because the light moved through regions with different histories. The universe is not a static arena containing galaxies flying outward from one central explosion. Space expands everywhere in the large-scale model. There is no center within ordinary three-dimensional space. The invariant speed constrains local causal motion. Cosmological distance is global and depends on the geometry of the expanding spacetime. This is one reason slogans fail. Nothing can move faster than light is safe when understood locally and causally. Applied without qualification to phase patterns, expanding coordinates, or changing definitions of distance, it becomes misleading. The speed of light is not one simple answer attached to every use of the word speed. It is a structural constant surrounded by several operational measurements. Even in vacuum, a subtle question remains. How is a one-way speed measured? To measure the time for light to travel from point A to point B, one needs a clock at A and a clock at B. The clocks must be synchronized. But synchronizing distant clocks already requires a convention or a signal whose travel time is understood. Einstein's standard convention sends light from A to B and back, then defines the distant clock so that the outward and return journeys take equal times. With this synchronization, the one-way speed of light is c in every inertial direction. The round-trip speed can be measured using one clock. Send light to a mirror and record the total time when it returns. Experiments constrain this two-way speed and its isotropy with extraordinary precision. Could someone choose a different synchronization convention and assign unequal one-way speeds while preserving the same round-trip result? Mathematically, alternative coordinate conventions can be constructed. They do not alter observable causal relations or experimental predictions. They change how distant times are labeled. This does not mean special relativity is arbitrary. The invariant space-time interval, the round-trip light speed, time dilation between reunited clocks, particle dynamics, and causal structure remain physical. The convention concerns the coordinate assignment of simultaneity at separated locations. The issue reveals how deeply time measurement depends on light. To say that two distant clocks show the same time is not a primitive fact. It is a procedure. Modern networks synchronize clocks using radio, optical fibers, transported atomic clocks, satellite links, and relativistic corrections. Every practical method rests on a model of signal propagation and gravitational environment. The speed of light is not merely measured by clocks. It helps define what distant clocks mean. The most famous appearance of c is not written as a speed at all. E equals mc squared. The equation is so familiar that it can seem like a logo for physics. Its real meaning is more specific and more powerful than the slogan that matter can turn into energy. A massive object at rest possesses energy simply because it has mass. This rest energy remains even when the object has no motion relative to an observer, no heat added, and no chemical fuel being burned. 1 kilogram of rest mass corresponds to almost 90 quadrillion joules. The number is enormous because c is enormous and appears squared. But an ordinary kilogram cannot be casually converted into that energy. Conservation laws, available reactions, and the structure of matter determine what fraction can be released. Chemical reactions rearrange electrons and alter mass by amounts too small for ordinary scales to notice. Nuclear reactions rearrange nuclei and produce much larger differences in binding energy. In nuclear fission, a heavy nucleus splits into more tightly bound products. The total rest mass of the products is slightly smaller than the original system. The difference appears as kinetic energy, radiation, and heat. In hydrogen fusion, for hydrogen, nuclei eventually form helium. The helium and accompanying products have about 0.7% less mass than the starting hydrogen. That mass difference supplies the energy of stars. The Sun converts roughly 4 million tons of mass into radiant energy every second. It does not destroy 4 million tons of ordinary matter while leaving nothing behind. A much larger amount of hydrogen is transformed into helium, and the difference in binding energy appears as light, neutrinos, and particle motion. The Sun becomes lighter because energy leaves it. Energy itself gravitates and contributes to inertia. Heat a sealed box, and its total mass increases by the added energy divided by c squared, though the change is tiny. Compress a spring, and the system gains mass. Charge a battery, and it becomes imperceptibly heavier than when discharged. Mass is not a separate substance hiding inside energy. Rest mass is a property of the total energy and momentum of a system. A box containing photons can have mass even though each photon has 0 rest mass. If 2 photons move in opposite directions, their momenta cancel in the box's center of momentum frame while their energies remain. The system as a whole has invariant mass. This is another way the speed of light connects concepts that once seemed separate. It converts temporal and spatial units in spacetime. It converts energy and momentum in the relativistic relation. It converts rest mass into an energy scale. Physicists often simplify equations by choosing units in which c equals 1. This does not claim that light moves at 1 meter per second. It means distance and time are measured in compatible units, such as seconds and light seconds. So the conversion factor disappears from the written equations. In those units, mass and energy can be expressed with the same unit. The simplification reveals that c behaves less like the speed of a vehicle and more like the number used when converting between meters and seconds inside spacetime geometry. Its numerical value of 299 million meters per second depends on human units. Choose kilometers and the number changes. Choose miles and it changes again. Measure distance in light seconds and time in seconds, and the value is 1. The physically meaningful statement is not that nature prefers a large decimal number. It is that an invariant finite speed links space and time. If the universe had no such finite invariant speed, its causal structure would differ. The classical limit of relativity can be imagined as c becoming infinitely large. In that limit, simultaneity becomes universal, time separates from space, and velocity addition returns to its simple Newtonian form. Our universe does not live in that limit. At the speeds of people, aircraft, and planets, c is so much larger that Newtonian physics works extremely well. The relativistic structure remains present but almost hidden. Particle accelerators reveal it directly. An electric field does work on a charged particle. At low speed, added energy produces a noticeable increase in velocity. As the particle becomes relativistic, the added energy increasingly appears as momentum and total energy rather than a comparable increase in speed. Protons in the Large Hadron Collider move within an extraordinarily tiny fraction of c. Increasing their energy greatly does not allow them to pass the boundary. It allows collisions to create heavier particles and probe smaller scales. A proton at nearly c still measures a nearby photon at c in its own instantaneous inertial frame. The gap in speed becomes small in the laboratory frame, but never disappears through finite acceleration. Cosmic rays push particles to even greater energies. The most energetic known cosmic rays carry macroscopic amounts of kinetic energy in a single atomic nucleus. Their speeds differ from c by unimaginably small fractions. Still, they remain massive and time-like. Neutrinos were once thought to be massless. Oscillation experiments showed that at least some neutrino mass states have non-zero mass. They therefore travel below c, although ordinary neutrinos are so light and energetic that the difference is minute. A supernova can emit neutrinos and light at different stages. Comparing arrival times places limits on neutrino speed and mass, but source physics must be understood. A delay does not automatically measure propagation alone. Every particle becomes a clock if it decays, oscillates, or changes in a predictable way. Relativity turns motion into a comparison of clocks. For a spacecraft traveler, the same mathematics opens a path to distant stars that is both hopeful and severe. Suppose a craft accelerates gently for a long time. Its speed relative to Earth rises. The crew's proper time remains normal. Earth clocks and ship clocks increasingly disagree. From Earth's frame, reaching a distant star cannot take less than the distance divided by c, apart from the acceleration and deceleration details. From the ship's frame, length contraction reduces the distance along the direction of travel. A journey across thousands of light years could, in principle, fit within one human lifetime of ship time if acceleration, energy, and survival problems were solved. Meanwhile, thousands or tens of thousands of years would pass in the galaxy's rest frame. This is genuine travel into the future. The crew does not exceed light speed. They follow a time-like path inside the light cone and age less than observers who remain on a different path. The so-called twin paradox captures the idea. One twin departs at high speed, changes direction, and returns younger than the twin who stayed home. The situation is not symmetric because the traveling twin changes inertial frames and follows a different space-time path. The difference can be calculated without mystery. It is the relativistic version of two routes having different lengths, except the quantity accumulated is proper time. Atomic clocks carried on aircraft and satellites show smaller versions of this effect. Speed slows their accumulated time relative to clocks on the ground. Gravity changes it as well. A complete comparison requires both special and general relativity. For interstellar travelers, the equations are kinder than the engineering. Accelerating a macroscopic craft to a large fraction of c requires tremendous energy. The kinetic energy must be supplied, and similar energy may be needed to slow down. Propulsion must carry fuel or receive energy externally. Waste heat must be removed. Collisions become dangerous. At ordinary speed, a grain of dust is harmless. At relativistic speed, the same grain carries explosive energy in the spacecraft frame. Individual hydrogen atoms in interstellar space become a beam of high-energy radiation. Cosmic microwave background photons are blue-shifted ahead of the craft. Shielding adds mass, and added mass increases the propulsion requirement. A near-light speed window would not show a calm starfield. Relativistic aberration concentrates the apparent directions of incoming light toward the forward direction. Doppler shift raises frequencies ahead and lowers them behind. Visible light from the front can shift into ultraviolet or X-rays. Light behind can move toward infrared and radio. Brightness changes through relativistic beaming. The universe would appear compressed into a brilliant, dangerous region ahead, with darkness and redshift behind. These effects are not caused by the traveler almost catching photons. Every local measurement of each photon still gives C. The changes concern frequency, direction, and energy. A photon emitted ahead by the ship moves away at C according to the crew and C according to Earth. The observers disagree about its frequency and about intervals between emissions, not about the local vacuum speed. Relativistic Doppler shift is therefore another place where the invariant speed reorganizes what can vary. Sound from an approaching source becomes higher because wavefronts are compressed in the medium. Light also shifts, but the relativistic result includes time dilation and does not require an ether. Source and observer motion enter through space-time geometry. Astronomers use these shifts to measure motion across the cosmos. Spectral lines from receding galaxies are redshifted. Binary stars reveal orbital speeds. Hot gas near black holes produces broadened and shifted lines. Relativistic jets advertise their orientation through beaming. The constant that prevents us from catching light also allows light to become a precise messenger of motion. The speed of light is so large that daily life can ignore its travel time. A conversation across a room feels immediate. A lamp seems to illuminate a wall at once. Electrical devices respond quickly enough that the delay is hidden beneath human perception. Modern technology operates on smaller timescales. Light travels a little less than 30 centimeters in 1 nanosecond. A timing error of only a few nanoseconds becomes a distance error of about a meter. Satellite navigation is built around this fact. A navigation satellite broadcasts a radio signal containing the time of transmission and information about its orbit. A receiver compares the transmitted time with the arrival time. Multiplying the delay by C gives an apparent distance to the satellite. One distance places the receiver somewhere on a sphere around one satellite. Several satellite signals allow the receiver to solve for position and for the error in its own clock. The calculation requires exquisite timing. Atomic clocks aboard satellites provide stable reference signals. Ground systems monitor their orbits and time standards. The receiver in a phone does not contain an equally capable atomic clock, so it uses signals from at least 4 satellites to solve for 3 spatial coordinates and an unknown clock offset. Relativity enters twice. The satellites move relative to the ground, producing special relativistic time dilation that makes their clocks run more slowly than comparable ground clocks. They also orbit higher in Earth's gravitational field, where general relativity predicts their clocks run faster than clocks deeper in the gravitational potential. The gravitational effect is larger for typical navigation satellites, so the net satellite clock rate differs from the rate required for the system. Corrections are built into the design. Without relativity, positioning errors would accumulate rapidly. The route displayed on a phone, the timing of financial networks, power grids, telecommunications, surveying, aviation, and scientific instruments all depend on a theory once dismissed by some as remote abstraction. The invariant speed has become infrastructure. It also helps define distance itself. For centuries, length standards were physical objects or natural artifacts. A meter could be represented by marks on a metal bar kept under controlled conditions. Later, it was linked to a specified wavelength of light emitted by krypton. As laser frequency measurements and atomic timekeeping improved, scientists could determine light's vacuum speed so precisely that the uncertainty in the meter standard became the limiting factor. In 1983, the international definition was reversed. The numerical value of c in meters per second was fixed. The meter became the distance traveled by light in vacuum during 1 second divided by the fixed numerical value assigned to c. The modern formulation defines the meter by taking c to have that exact numerical value, with the second defined through a cesium atomic transition. This means no future experiment will report a more accurate value of c in SI meters per second. The value is exact by definition. Experiments can test whether light propagation follows relativity, whether different frequencies behave differently, whether direction matters, or whether new physics creates tiny violations. They can improve the realization of the meter, but they do not refine the fixed decimal value within the SI. This can sound circular. If c defines the meter, how can the constancy of c be tested? The test concerns relationships, not the arbitrary size of a unit. Researchers compare clocks, resonant cavities, particles, astronomical signals, and propagation directions. They search for changes with orientation, time, energy, gravitational environment, or source motion. A violation would appear as inconsistency among physical processes, not as a revised ruler reading alone. Precision experiments have found no established breakdown of local Lorentz invariance. The symmetry has been tested using optical cavities, atomic clocks, particle decays, cosmic rays, and astrophysical observations across enormous energy ranges. Every successful test tightens the possible space for alternatives. Yet the search continues because an exact principle can reveal deeper physics through the smallest deviation. Quantum gravity proposals sometimes suggest minuscule modifications at energies far beyond accelerators. Light from distant gamma-ray bursts can test whether high-energy photons accumulate different travel times across billions of light-years. So far, no convincing energy-dependent vacuum speed has emerged. The finite speed of light also creates ordinary engineering delays that cannot be eliminated. A command sent to the moon requires a little more than a second to arrive. A conversation with astronauts there contains a noticeable pause. At Mars, the one-way delay ranges from several minutes to more than 20 minutes, depending on the planet's positions. A rover cannot be driven like a remote-controlled car. It receives instructions, navigates hazards autonomously, and sends results back later. At Jupiter, the delay is tens of minutes. At Saturn, it is more than an hour. At the outer edge of the solar system, it becomes many hours. No faster processor can remove this delay. Better compression, prediction, and autonomy can make communication more useful, but information still crosses the distance at no more than c. Interstellar communication is slower on human scales. A message to the nearest star system needs more than 4 years. A reply needs another 4. A civilization 1,000 light-years away could receive a transmission from Earth's Middle Ages and answer a future society that no longer resembles ours. Conversation becomes archaeology conducted through signals. The speed of light is extremely fast locally and extremely slow astronomically. It circles Earth several times in 1 second, yet it needs years to move between nearby stars and tens of thousands of years to cross the galaxy. This tension shapes every dream of exploration. The same number that makes a room feel instantaneous makes the cosmos feel ancient. It also protects us from direct knowledge of the present elsewhere. When a telescope observes a star 100 light-years away, there is no method for asking what the star is doing now in an Earth-based sense. The available image left a century ago. A supernova could already have occurred, or a planet could have changed, while the light carrying that news remains in transit. The delay is not a flaw in the telescope. It is the causal structure of observation. Every astronomical image is an arrangement of different pasts. The moon appears a little more than a second old. The sun appears minutes old. Jupiter appears tens of minutes old. Nearby stars appear years old. Distant galaxies appear millions or billions of years old. A deep field image is not a photograph of one universal moment. It is a layered history assembled on one detector. The farther away astronomers look, the earlier in cosmic history they see. The finite speed becomes a time machine for observation. Telescopes do not travel into the past. Ancient light arrives in the present. By collecting it, scientists watch galaxies form, quasars ignite, and the universe evolve. If light were instantaneous, distance would not provide this natural record. The sky would show everything at one universal now, if such a now existed. Cosmology would lose its deepest archive. Because C is finite, the universe preserves its history in transit. Gravity adds a new layer because space-time is no longer flat. Special relativity describes inertial observers in regions where gravity can be neglected. General relativity extends the structure by allowing matter and energy to curve spacetime. The invariant speed remains local. An observer freely falling beside a light beam measures that beam moving at c. This remains true near a planet, near a neutron star, and at the event horizon of a black hole, provided the measurement is made locally with an ordinary clock and ruler. Distant comparisons become more complicated. Imagine sending radar pulses toward a planet when the path passes close to the sun. The signal takes slightly longer than a simple flat space calculation predicts. This is the Shapiro delay. Curved spacetime changes the relation between coordinates and measured intervals along the route. The light has not become tired or slowed by resistance. It follows a null path through a geometry shaped by the sun. The same geometry bends light. During a solar eclipse, the apparent positions of stars near the sun shift because their light travels through curved spacetime. Galaxy clusters bend light from more distant galaxies into arcs and multiple images. Dark matter is mapped through this gravitational lensing even though it emits no light of its own. The invariant speed does not force rays to follow Euclidean straight lines. It forces them to follow the local causal structure. Near a black hole, coordinate descriptions can create the strongest illusion of changing light speed. A distant observer using a certain time coordinate sees an infalling object slow as it approaches the event horizon. Its signals become increasingly redshifted and delayed. Light sent outward from near the horizon takes longer and arrives with lower energy. The object never appears to cross within finite distant coordinate time in that description. The falling observer experiences something different. For a sufficiently large black hole, crossing the horizon can occur without a sudden local event. Light nearby still passes at c. The observer's clock continues ticking. The horizon is crossed in finite proper time. These accounts are compatible because they assign time differently across curved spacetime. No single global clock provides an unquestioned master description. In the simplest classical geometry of a non-rotating black hole, the future light cones inside the horizon tilt so that all future directed time-like and light-like paths move toward smaller radius and ultimately toward the singular region. Escaping would require moving outside the local light cone, not merely firing a stronger engine. The black hole is black because of causal geometry. The phrase escape velocity exceeds light speed can be a useful analogy, but it is not the full, general relativistic explanation. Nothing at the horizon locally attempts to outrun a Newtonian pull. The horizon marks a boundary from which no future directed causal path reaches the distant exterior. Light defines the boundary, but light is not exempt from it. Black holes also reveal how time and frequency depend on gravity. A photon climbing away from a massive body is received at lower frequency. The emitter and receiver disagree about the photon's energy because they use clocks ticking at different gravitational rates. In a stationary spacetime, one can describe conserved quantities along the path, but local measurements vary with the observer. The photon does not steadily spend a fuel supply while rising. The frequency shift belongs to the comparison of clocks in motion across geometry. Gravitational redshift has been measured on Earth. Clocks at different heights tick at different rates. Modern atomic clocks are sensitive enough to detect height differences on human scales. The speed of light ties these clock comparisons to distance, navigation, and gravity. General relativity also predicts gravitational waves, traveling disturbances in space-time curvature. When massive objects accelerate asymmetrically, especially compact objects such as black holes and neutron stars, they can radiate gravitational waves. The waves stretch and compress distances by tiny amounts as they pass. LIGO and Virgo detect these changes using laser interferometers. Mirrors are separated along perpendicular arms. A passing gravitational wave changes the relative optical path lengths, shifting the interference pattern. Light measures a wave in space-time that propagates at the same invariant speed. The neutron star merger observed in August 2017 created one of the most powerful tests. Gravitational waves traveled from a galaxy about 130 million light-years away. A gamma-ray burst followed shortly after. Across that enormous journey, the speeds agreed to within extraordinarily tight limits. This result eliminated or severely constrained many modified gravity models in which gravitational waves and light propagate differently. The closeness is not merely a coincidence between two kinds of wave. In general relativity, both follow the null structure of spacetime. Massless fields respect the same causal cones. Could gravity ever propagate instantaneously while light remained finite? Newton's original theory effectively treated gravitational influence as instantaneous. If the sun moved, the force law seemed to update everywhere at once. This raised conceptual problems even before relativity. In general relativity, the gravitational field is not a force transmitted through static space. It is the dynamical geometry. Changes propagate causally. Earth orbits within a gravitational spacetime shaped by the sun's current and past state. The situation cannot be reduced to aiming at a delayed visual position as though gravity were a stream of particles sent from where the sun appeared 8 minutes ago. The field around a steadily moving source contains velocity-dependent structure, and orbital dynamics remain consistent. Gravitational radiation carries changes away at sea. The speed of gravity therefore does not mean that planets chase outdated force arrows. It means disturbances and new information about the gravitational system respect the causal boundary. The same boundary operates around accelerating observers. An observer undergoing constant acceleration can develop a horizon. Light from sufficiently distant regions may never catch up. The horizon resembles, in some mathematical ways, a black hole horizon even though no black hole is present. This leads to the Unruh effect, in which an accelerating observer associates a thermal bath with a quantum field that an inertial observer describes differently. The effect is extremely small for ordinary accelerations, but it shows again that particles, vacuum, and horizons depend on the observer's motion while the causal structure remains consistent. Light's speed is invariant, yet what counts as a particle can change. In cosmology, horizons also appear without a collapsed star. An accelerating universe can possess a cosmic event horizon. Light emitted now from sufficiently distant regions may never reach us, even given unlimited future time, because the intervening expansion grows too rapidly. The horizon is not a wall at a fixed location. It is a statement about which world lines can ever exchange signals. Once again, C does not simply tell light how fast to move. It separates possible histories from impossible connections. The observable universe is a history of light cones. The universe is about 13.8 billion years old according to the standard cosmological model. It is tempting to multiply that age by C and conclude that the most distant observable matter must be 13.8 billion light-years away. The actual distance is much larger because space expanded while the light traveled. The matter that emitted the cosmic microwave background is now roughly 46 billion light-years away in present-day cosmological distance. The full observable region has a diameter of about 93 billion light-years. No object violated the local speed limit to reach that separation. The distance between us and the emitting matter increased during the journey. The light kept moving locally through each region at sea while the large-scale geometry evolved. This distinction creates several different horizons. The particle horizon marks the greatest present distance from which any signal could have reached us since the early universe. The cosmic event horizon, if the current accelerated expansion continues, concerns events whose signals can ever reach us in the infinite future. The surface of last scattering marks the origin of the cosmic microwave background, not because nothing existed before it, but because the young universe was opaque. Light scattered constantly from free electrons. When atoms formed about 380,000 years after the beginning, photons could travel freely. Those photons have stretched with expansion from visible and infrared energies into microwaves. They arrive from every direction as the oldest electromagnetic image available. There are earlier messengers in principle. Neutrinos decoupled when the universe was about a second old, creating a cosmic neutrino background that has not yet been directly detected. Primordial gravitational waves, if produced, could carry information from even earlier epochs. The electromagnetic horizon is therefore not the absolute horizon of all physics. It is the boundary set by transparency and light propagation for the messenger we currently image best. Every point in space has its own observable universe. A galaxy 10 billion light-years away is not standing near the edge of a sphere centered on us in any privileged cosmic sense. Observers there would see a different sphere centered on themselves. Some regions visible to them are permanently beyond our horizon, and some regions visible to us are beyond theirs. The universe may be much larger than the observable region and may be spatially infinite. Observation cannot decide the entire extent directly because information from beyond the horizon has not arrived. The phrase observable universe is therefore modest. It does not mean all that exists. It means all that can be connected to us by past directed causal paths under the cosmic history. Expansion can also carry galaxies across an event horizon. Their light becomes increasingly redshifted and faint. Signals emitted after a certain time never reach us. From our perspective, distant galaxies do not visibly strike a wall. Their future history fades and freezes into ever older, weaker information. Over immense time, if dark energy behaves like a cosmological constant, galaxies outside our gravitationally bound neighborhood will disappear from view. Future astronomers in the local group may see a much emptier cosmos. The speed of light remains unchanged, but the geometry removes potential signals from causal access. This creates a haunting possibility. There are events occurring now, in some cosmological coordinate sense, whose future light will never reach Earth. There are galaxies whose present state is not merely delayed, but permanently unknowable. The universe contains more happenings than any one observer can ever receive. Causality is local and finite. Yet the finite speed also makes cosmology possible. Because distant regions are seen at earlier times, surveys can compare galaxies across stages of evolution. Nearby galaxies show mature structures. More distant galaxies reveal younger populations. The deepest observations show the first few 100 million years. The telescope's field becomes a geological core drilled through time. Redshift provides part of the ordering. Expansion stretches wavelengths. A spectral feature emitted in ultraviolet may arrive in infrared. The amount of redshift relates to cosmic expansion, though converting redshift to distance requires a cosmological model. Light carries both the object's local physics and the history of the path. Dust absorbs and scatters it. Gravity lenses it. Expansion stretches it. Gas imprints absorption lines. Plasma delays radio frequencies. Each alteration can be treated as contamination or as information. The universe writes on the signal while it travels. The speed c determines the causal route, but not an unchanging travel environment. This matters when saying that we see the sun 8 minutes ago. The statement is excellent in the nearly static geometry of the solar system. Across cosmological distances, a single travel time and present distance are not simply related by distance equals c times time. Different definitions of cosmological distance answer different questions. How far was the galaxy when it emitted the light? How far is the matter now in a chosen cosmic time slice? How bright does it appear? What angular size does an object have? How long has the light traveled? These distances can differ because space-time expands. The invariant local speed remains simple while global distance becomes subtle. Even within the solar system, paths are not perfectly straightforward. Light from the sun takes a little over 8 minutes to reach Earth, but the exact time changes as Earth moves in its slightly elliptical orbit. Signals sent past planets experience gravitational delay. Plasma in the solar wind delays radio waves in a frequency-dependent way. Deep space navigation models these effects. A spacecraft's position is inferred from radio travel time, Doppler shift, and angular measurements. The equations account for planetary motion during the signal's journey and for relativistic corrections. When a command reaches a distant probe, the Earth has moved from where it was at transmission. The probe has moved too. Communication aims at where the receiver will be, and the returning signal aims at a future Earth. Every exchange is a prediction across a light cone. The speed of light also limits control. A robotic mission near Saturn cannot ask Earth for immediate help during a dangerous maneuver. By the time a problem is seen, the event happened more than an hour earlier. A reply takes another hour or more. The machine must survive on its own. Farther away, autonomy becomes essential. An interstellar probe receiving instructions from Earth decades after launch is always guided by an old version of home. Its reports describe an old version of the destination by the time they arrive. Causality turns distance into independence. This may shape the behavior of technological civilizations. A galactic society cannot operate as one instantly coordinated organism under known physics. Regions separated by thousands of light years cannot share a common political or cultural present. Information spreads as expanding shells. Decisions branch before replies return. A civilization might cross the galaxy while never existing as one simultaneous community. The speed limit does not prevent expansion through the galaxy over millions of years. It prevents immediate unity. The same would apply to any extraterrestrial signal. A deliberate transmission from a distant star is a message from the sender's past. By the time it arrives, the civilization may have changed or vanished. A reply addresses descendants. The silence of the sky cannot be interpreted as though everyone shares our present. Light makes the universe visible and keeps every distant world temporally separate. The desire to cross the limit has produced some of the most imaginative ideas in physics. Tachyons were proposed as hypothetical particles that always move faster than c, just as ordinary massive particles always move below it and massless particles move at it. In the mathematics of special relativity, a tachyon would not be accelerated through the light barrier from below. It would belong to a separate class. Slowing it towards c from above would require increasing energy, making the boundary unreachable from either side. No tachyon has been detected. The concept also creates severe problems with causality and quantum stability. In modern field theory, a quantity described as tachyonic often signals that an assumed state is unstable, not that an observable particle is literally traveling faster than light. Nature may use the mathematics to say that a system must reorganize, rather than to provide a superluminal messenger. Wormholes offer another possibility. General relativity permits geometries containing tunnels between distant regions of spacetime. A traveler entering one mouth could emerge from another without locally exceeding c along the path. The shortcut would make the effective journey faster than light traveling through the ordinary exterior route. The known solutions are problematic. A traversable wormhole appears to require exotic stress energy that violates familiar energy conditions. Quantum fields can produce small negative energy effects in restricted situations, such as the Casimir effect, but scaling and stabilizing them into a macroscopic tunnel is far beyond established physics. Wormholes can also become time machines if their mouths move relative to one another or experience different gravitational histories. The resulting causal loops suggest that quantum effects or deeper principles may prevent usable configurations. No astronomical observation has established the existence of a traversable wormhole. Black holes are not automatically wormholes to somewhere else. The idealized Einstein-Rosen bridge in certain mathematical black hole solutions is not a stable corridor an observer can cross and return through. Warp drives use a different strategy. Instead of moving a spacecraft through nearby space faster than c, a hypothetical warp geometry contracts space ahead and expands it behind. The craft remains locally inside a bubble, following a time-like path, while the bubble crosses large external distances effectively faster than light. The best-known example is the Alcubierre metric. It is a valid mathematical geometry if a suitable stress-energy distribution is supplied. That phrase contains the difficulty. The required matter includes negative energy densities in forms and amounts not known to be physically realizable. Some versions create horizons that prevent the crew from controlling the front of the bubble. Starting, steering, and stopping can demand information be placed where the craft cannot send it. The geometry may accumulate dangerous radiation and release it at arrival. Quantum inequalities may restrict the negative energy. Even improved theoretical versions remain far from engineering proposals. A mathematical solution to Einstein's equations is not automatically a constructible object. The equations relate geometry to stress energy. One can choose a geometry and calculate the extraordinary material it would require. Nature must still provide that material, allow it to remain stable, and permit it to be assembled causally. Warp drives and wormholes are valuable because they test the boundaries of theory. They show that the statement "nothing can travel faster than light" is more precise than an ordinary prohibition. Locally, no massive object outruns c. Global spacetime geometry can create shortcuts or expanding separations in equations. Whether those geometries can exist under physically reasonable conditions is another question. Quantum gravity may eventually change the discussion, but no established theory predicts a practical route. The safest current conclusion is that faster-than-light transport and communication are not known to be possible. Another speculative idea asks whether c itself could have been different in the early universe. A dimensional constant's numerical value depends on units, so saying c changed requires care. Physically meaningful tests compare dimensionless combinations or the relationships among clocks, rods, particle masses, and interactions. Some varying constant cosmologies have attempted to address early universe problems by changing effective propagation speeds or Lorentz symmetry. These models face theoretical and observational constraints and have not replaced inflation or standard relativity. The possibility is scientifically legitimate when formulated precisely. It is not evidence that light currently chooses different vacuum speeds at different times. Measurements of distant spectra test whether dimensionless constants, such as the fine structure constant, have changed. Laboratory clocks compare different atomic transitions over years. Astrophysical events compare high and low energy messengers across cosmic distances. No confirmed variation requiring a breakdown of local Lorentz invariance has emerged. What if C were smaller while all other physically meaningful relationships remained somehow comparable? The question cannot be answered by changing one decimal number alone. C connects electromagnetism, relativity, units, and causal structure. Altering it while holding everything else fixed may be mathematically inconsistent or dependent on the chosen units. A universe with a different dimensionless balance among electromagnetic strength, particle masses, and propagation scales could form atoms, stars, and chemistry differently. If the causal speed were much lower relative to characteristic motions, relativistic effects would become common. A car might experience significant time dilation. Planetary orbits could require relativistic treatment. Communication delays across Earth would be obvious. If it were effectively infinite, simultaneity would become absolute, and the relativistic connection between space and time would disappear in the classical limit. Our universe places ordinary life in a slow regime. Human motion is tiny compared with C. Even Earth around the Sun moves at only about 1/10,000th of the invariant speed. The solar system can often be understood with Newtonian mechanics, while light and precision clocks reveal the deeper geometry. This separation may help stable structures form and allow local cause and effect to feel immediate while preserving a finite cosmic history. It is tempting to ask why C has the value it does. In meters per second, the question partly asks why humans chose these units. The exact decimal contains conventions. A more meaningful question asks why space-time possesses a finite invariant speed and why dimensionless constants take the values that determine the behavior of matter. Current physics describes these features extraordinarily well. It does not derive every constant from a deeper confirmed theory. The standard model of particle physics contains measured parameters. General relativity takes C as part of its structure. Efforts to unify gravity and quantum theory search for deeper explanations, but no experimentally confirmed framework shows why all constants must have their observed relationships. The mystery is not a missing mechanical cause pushing light to a particular velocity. It is why reality has Lorentzian geometry at all. Why does space-time distinguish time-like, light-like, and space-like intervals? Why are causal cones finite? Why do massless excitations lie on their boundaries? These questions reach beyond measuring a beam. They ask why the universe permits a coherent ordering of influence in this form rather than another. The success of relativity suggests that C is not attached to an invisible medium. It is a symmetry scale. Lorentz symmetry says that the laws of physics do not select one inertial frame as truly at rest. Space and time mix under changes of motion in exactly the way required to preserve the space-time interval and the causal cone. The invariant speed is the fixed point of velocity transformation. Observers disagree about distances, durations, energies, and frequencies. They agree about C and about whether an interval is time-like, space-like, or light-like. That agreement is more fundamental than agreement about the position of a moving object. It defines the common structure beneath different descriptions. A world without a preferred state of rest initially seems less ordered. There is no stationary cosmic floor. Yet relativity replaces absolute motion with stronger invariance. No observer owns the true space and time. All share space-time. Einstein later recalled wondering what would happen if he chased a beam of light. In classical thinking, a sufficiently fast observer might see the electromagnetic wave slow. At exactly the wave speed, the observer might expect a frozen pattern of electric and magnetic fields hanging in space. Maxwell's equations do not contain such a stationary light wave in vacuum. The contradiction pointed toward the failure of classical velocity addition, not toward a special material hidden behind light. No massive observer can occupy the imagined frame. The closer a spacecraft comes to sea, the more unusual its comparison with Earth becomes, but the onboard measurement of light remains ordinary. A lamp flashes. The beam crosses the cabin at sea. A mirror reflects it. The crew calculates the same result as before launch. Earth observers also measure that beam at sea. They preserve agreement by disagreeing about the cabin's length, the clock intervals, and which distant events are simultaneous. The relativity of simultaneity is often treated as the least dramatic effect because it cannot be photographed as easily as a shortened ruler. It is the effect from which many paradoxes obtain their force. Imagine a long spacecraft moving past Earth. At the center of the craft, a flash sends light toward the front and rear. In the craft's frame, the ends are equally distant, so the pulses arrive together. In Earth's frame, the front moves away from its pulse while the rear moves toward the other. It seems obvious that the rear should be struck first. It is. Both observers remain correct because the events at the two ends are simultaneous in the craft frame and not in the Earth frame. The light speed remains c in each description. The disagreement is not repaired by waiting for signals and correcting travel time. It is built into the coordinates each observer constructs with synchronized clocks. This can become physical when forces act across extended objects. Suppose a line of rockets begins accelerating. If every rocket starts simultaneously according to one initial inertial frame and maintains the same coordinate acceleration, the distance between neighboring rockets in that frame can remain fixed. But the accelerating rocket's instantaneous rest frames change. In those frames, maintaining the original proper separation requires a different acceleration program along the line. If the rockets are connected by a thread, the thread can stretch and break. This is Bell's spaceship paradox. It shows that length contraction is not a simple pressure exerted on moving objects. The stress depends on how acceleration and simultaneity are organized. Another puzzle uses a pole and a barn. A pole moving rapidly is length contracted in the barn's frame and can fit momentarily between two doors. In the pole's frame, the barn is even shorter, so how can both doors close around it? The answer is simultaneity. The doors close together in the barn frame. They do not close together in the pole frame. There is no frame-independent event in which the entire pole is at rest inside a shorter barn. Relativity avoids contradiction by denying universal simultaneity, not by allowing one observer's measurements to be less real. These puzzles may sound engineered, but nature performs related operations in particle accelerators. Electric fields are timed to bunch particles. Magnets guide beams whose internal distances and frequencies depend on frame. Synchrotrons keep particles in phase with oscillating fields by using relativistic dynamics. The equations must be right to extraordinary precision or the beam is lost. The muon storage ring offers an especially clear clock. Muons circulate near C while magnetic fields bend their paths. Their decay times are dilated. Their spin motion includes relativistic effects. Measurements can test particle properties and search for new physics. Every lap is a repeated refusal to cross the light boundary. Circular motion also introduces acceleration even when speed remains nearly constant. The particle's direction changes. An observer tied to the particle is not one global inertial frame around the ring. This matters when applying simple time dilation. Comparing reunited clocks requires integrating proper time along each path. The result is not decided by saying each sees the other slow and stopping there. During inertial separation, each can describe the other's moving clock as slow. When one traveler turns around, the change of frame shifts the traveler's assignment of simultaneity across distant Earth. The reunion produces an invariant age difference. Acceleration identifies the asymmetry operationally, but the accumulated proper times can be calculated from the geometry of the paths. This offers a better understanding of time travel into the future. A traveler does not cause Earth time to speed up through a mysterious force. The traveler follows a path with less proper time between departure and reunion. In flat space-time, the inertial path between two time-like separated events has the greatest proper time. Departing, turning, and returning reduces it. This is the reverse of ordinary Euclidean intuition, where a straight path is shortest. Lorentzian geometry treats time differently from space. The minus sign in the space-time interval is not a minor mathematical detail. It creates light cones and allows different paths to accumulate different durations. C converts the time interval into distance units so the terms can be compared. The invariant interval remains the same for all inertial observers, even though each splits it differently into spatial separation and temporal separation. For nearby events in one spatial direction, the structure can be expressed as the square of c times the time difference minus the square of the distance difference. If the result is positive under one common sign convention, the interval is time-like. A massive traveler can connect the events. If it is zero, the interval is light-like. A massless signal can connect them. If the spatial part dominates, the interval is space-like. No causal signal limited by c can travel between them. Observers may disagree about the numerical time and distance separately. They agree on the intervals category. This is the invariant heart of special relativity. The term speed of light can make c sound secondary, as though physicists observed a fast object and built geometry around its behavior. Historically, light guided the discovery. Structurally, massless light follows a geometry that would exist as causal structure even if human eyes had never evolved, and even if electromagnetism were studied through radio alone. If photons somehow possessed a tiny rest mass, electromagnetic waves would no longer propagate exactly on the same null cones in the usual way. Experiments and astronomical observations place extremely strong limits on photon mass. No non-zero value has been established. The remarkable agreement between light and the causal structure remains. Other fields reveal it. Gravitational waves travel at c to high precision. Gluons are massless in the underlying theory, although confinement prevents isolated gluons from crossing macroscopic vacuum. Hypothetical exactly massless particles would also follow null paths. The speed limit is therefore not enforced by photons patrolling the universe. Photons are witnesses. This changes the answer to a familiar question. Why does light travel so fast? If the question means why does visible electromagnetic radiation have a particular vacuum speed, Maxwell and relativity explain that it is a massless field propagating along the null structure. If the question means why is c finite, and why does space-time have that structure, present theory describes rather than fully explains the foundation. And if the question means why is the number so large, the answer depends partly on meters and seconds. 1 second is enormous compared with the time light needs to cross human distances. 1 meter is small compared with the distance light covers during a second. The decimal reflects that mismatch. In Planck units, c is 1. In light years and years, it is 1. In meters and seconds, it is almost 300 million. A dimensionless quantity would not change when units change. The fine structure constant, for example, describes electromagnetic coupling without carrying meters or seconds. Questions about why nature has a particular dimensionless value are more direct. Still, the fixed SI number has practical beauty. 1 second is defined through a specified number of oscillations associated with cesium. Once that clock is established, C tells us how to realize distance. Time becomes a ruler through light. A metrology laboratory can stabilize a laser's frequency, measure its wavelength, and connect length to atomic standards. Interferometers compare distances by counting wave cycles. Laser ranging measures the moon's recession using pulses reflected from mirrors left by Apollo missions and lunar rovers. The round-trip travel time reveals distance to millimeters under careful modeling. Very long baseline interferometry combines radio telescopes separated across Earth. Signals from distant quasars reach each telescope at slightly different times. Comparing them provides exquisite angular resolution, Earth orientation measurements, and geodesy. The finite arrival delay becomes a ruler spanning a planet. Gravitational wave detectors use kilometer-scale laser paths to detect changes far smaller than an atomic nucleus relative to the arm length. The instrument does not measure C by watching one pulse race a stopwatch. It uses light's stable phase and causal propagation to compare spacetime paths. From phone navigation to black hole mergers, measurement rests on the same invariant. The number known by schoolchildren is working quietly inside the definition of where things are. Light itself becomes stranger when the classical wave picture meets quantum theory. Maxwell described a continuous electromagnetic field. Quantum physics revealed that interactions exchange energy in discrete amounts called photons. A photon is not a miniature glowing bead following a perfectly defined classical path in every circumstance. It is a quantum excitation of the electromagnetic field. Its energy is related to frequency by Planck's constant. Its momentum is related to wavelength. Higher frequency light carries more energy per photon. Gamma-ray photons are more energetic than X-ray photons. Visible photons are more energetic than infrared and radio photons. All travel at sea in vacuum, yet their interactions with matter differ dramatically because their energies and wavelengths differ. Radio waves can pass through materials that block visible light. X-rays penetrate tissue but are absorbed more strongly by bone. Gamma rays can create particle-antiparticle pairs under suitable conditions. The invariant propagation speed does not make all electromagnetic radiation behave identically. The wave and particle descriptions are not competing stories from which nature chooses one at a time. They are classical approximations to a quantum field whose behavior does not fit ordinary categories. A single photon can produce an interference pattern statistically across repeated experiments. Which path information changes the pattern? Entangled photons display correlations that challenge classical pictures. Yet every controllable influence still respects the causal structure. Quantum electrodynamics combines quantum theory with special relativity. It is among the most precisely tested theories ever constructed. Its calculations include virtual processes that cannot be interpreted as ordinary particles traveling along detectable paths. Virtual photons appear inside perturbative mathematical descriptions of interactions, but they are not faster than light messages escaping into a detector. Confusion often begins when an internal calculation is treated as a literal movie. Relativistic quantum field theory protects causality through the structure of observable operators. Measurements at space-like separation cannot be used for causal influence outside the light cone. Quantum uncertainty does not dissolve the boundary. Vacuum is also not simple emptiness. Quantum fields exist in their lowest energy states. Fluctuations and correlations remain. Boundaries can alter allowed modes, producing effects such as the Casimir force. Particles can appear for accelerating observers or in strong, changing fields. But the quantum vacuum does not supply an ether that selects absolute rest. Lorentz invariance remains central. The vacuum state of a relativistic field does not behave like a wind through which Earth moves. This is one of the reasons attempts to revive the old luminiferous medium fail. A material medium has a rest frame and can be detected through anisotropic propagation. The relativistic vacuum is governed by symmetry rather than mechanical substance. Some modern theories do consider fields that acquire background values and might select preferred structures. Experiments search for the resulting Lorentz violations. None has become established. The absence of an ether did not mean space contains nothing. It meant electromagnetic propagation does not require the kind of mechanical medium 19th century physics expected. Light can cross interstellar vacuum because the electromagnetic field is a fundamental part of the universe. A changing field propagates according to its equations. There is no hidden air for the wave to shake. The classical relation between electric and magnetic fields also depends on motion. An observer may describe a configuration as mostly electric. Another moving observer can measure a mixture of electric and magnetic fields. The fields transform into one another under Lorentz transformations. Electricity and magnetism are therefore not completely separate phenomena. A current-carrying wire illustrates this. In one frame, magnetic forces act on moving charges. In another frame, length contraction changes charge densities, producing an electric description. The same physical interaction is divided differently between electric and magnetic components. The invariant speed enters the transformation. Maxwell's unification and Einstein's relativity fit because electromagnetism already carried the new geometry within its equations. The speed predicted for electromagnetic waves was the clue, but the deeper unification says that observers disagree about electric and magnetic fields while agreeing on covariant electromagnetic laws. Light is what the electromagnetic field does when a disturbance propagates freely. This also explains why moving toward a source does not increase the measured vacuum speed. The observer measures a higher frequency and shorter wavelength instead. The relationship frequency times wavelength equals c remains. Move toward the source and wave crests arrive more often. The wavelength in the observer's frame is reduced. Their product still yields c. Move away and the frequency falls while the wavelength grows. Again, the product remains c. The wave adapts through Lorentz transformation. A sufficiently energetic observer moving toward a low-frequency photon can measure it as high-frequency radiation. A radio photon in one frame could be a microwave or higher-energy photon in another. There is no absolute frequency attached independently of the observer. The photon remains massless. Its energy and momentum change between frames, but the relation between them remains E equals pc. This has dramatic consequences for the early universe. Cosmic microwave background photons were once much more energetic. Expansion stretched their wavelengths and lowered their frequencies. They did not slow down. They lost energy relative to comoving observers because the space-time geometry changed during propagation. As the universe expands, there may be no simple global energy conservation law for the photon field in the same form used in a static spacetime. The redshift is not friction against space. It is the evolution of the metric and the changing relationship between successive observers. The speed stays local and invariant while energy changes. Near a black hole, a similar pattern appears as gravitational redshift. Light climbing outward is measured at lower frequency by distant stationary observers. Falling light can be blue-shifted. Again, c remains local. This separation between speed and energy is easy to miss because everyday objects usually gain energy by moving faster. A photon cannot increase its speed. Give it more energy and its frequency rises. Its momentum increases. Its color may change. The velocity in vacuum remains c. A massive particle uses energy partly to increase speed, then increasingly to increase relativistic momentum as it approaches the limit. A massless particle starts on the boundary and uses energy entirely through frequency and momentum. The two cases reveal why c is not simply the top mark on one common speedometer. Massive and massless things inhabit different kinds of world line. Could a photon ever be slowed in vacuum by becoming tired? Observations from distant galaxies show no ordinary loss of vacuum speed with age. Cosmological redshift lowers energy, not local propagation speed. Scattering through matter or plasma can delay a signal, but between interactions the local causal structure remains. The phrase tired light was once proposed as an alternative explanation for cosmological redshift. In such models, photons would lose energy through unknown interactions during travel without expansion. These ideas fail to match multiple observations, including time dilation and distant supernova light curves, the cosmic microwave background, and the detailed relationship between brightness and redshift. Expansion, not simple fatigue, explains the broad evidence. Light can travel for billions of years without a clock attached to it, and without gradually dropping below C. Its frequency can be stretched to radio waves. Its direction can be bent by gravity. Its path can be interrupted by absorption and scattering. Its causal character remains null. This persistence is what allows ancient photons to carry information across cosmic history. A photon reaching a telescope may have last interacted with matter when the universe was young. Its wavefront has expanded across immense regions. Only a tiny portion enters the detector. The absorbed energy releases an electron, changes a current, or alters a molecule. An event billions of years ago becomes a local signal now. The connection is limited by C, but it is not weakened into meaninglessness by the journey. The universe is observable because light remembers. Consider one pulse leaving the sun. In the dense solar interior, the energy does not travel straight outward as one unchanged photon. Radiation interacts repeatedly with plasma. Energy is absorbed, emitted, scattered, and transported through a vast, opaque interior. The journey from the core to the visible surface can take an extremely long time. At the photosphere, a photon begins a much clearer path through space. It crosses the gap to Earth in a little more than 8 minutes. Locally, every freely falling observer along the route measures the vacuum speed c. The photon passes through curved spacetime created by the sun and planets. It enters Earth's atmosphere, where the electromagnetic wave interacts with molecules and its effective propagation becomes slightly slower than in vacuum. Refraction bends the path. Turbulence shifts the apparent position of the solar image. In glass, the wave slows further. A lens redirects it onto a retina or detector. At no point does one simple phrase describe the entire journey. The energy history in the sun is not a single photon patiently bouncing for thousands of years. The vacuum leg follows a null path. The atmosphere and glass create coupled light matter propagation. Gravity shapes geometry. The detector absorbs the final quantum and converts it into another process. Yet C remains the organizing constant. It sets the vacuum path, the causal delay, the relation between frequency and wavelength, and the geometry used to interpret every observer's measurement. Now imagine chasing the pulse. A spacecraft accelerates away from the sun. The light becomes redder behind the ship. Its energy falls in the traveler's frame. The wavelength grows. The speed does not become c minus the spacecraft's speed. Turn the craft around and race toward the pulse. It becomes bluer and more energetic. The speed does not become c plus the spacecraft's speed. The observer's clock, ruler, frequency measurement, and simultaneity transform together. This is why the invariant speed can feel impossible when one part of the problem is held fixed. Common sense keeps time universal and distance universal, then tries to fit c into the remaining space. Relativity changes the foundation. There is no universal time interval between separated events. There is no universal spatial distance between them. There is no universal division of the electromagnetic field into electric and magnetic parts. There is no universal frequency for one photon. There are invariants connecting the different descriptions. The speed c is one of them. The spacetime interval is another. Rest mass is another. The laws remain covariant even as measured components change. The universe is not inconsistent because observers disagree. Their disagreements follow exact rules. A person standing on Earth, a pilot in a fast spacecraft, and an observer falling toward a black hole can assign different coordinates to the same events. Each uses local clocks and rulers. Each measures nearby light in vacuum at sea. When their data are translated correctly, they describe one spacetime. That is a more subtle form of objectivity than one universal viewpoint. It replaces the imagined eye of the universe with relationships all observers can test. The speed of light is therefore not what its name first suggests. It is not merely the velocity of visible brightness. It is not a property caused by light pushing through a vacuum medium. It is not a barrier that a sufficiently powerful engine nearly punches through before being repelled. It is not the speed at which every apparent pattern must move. It is not reduced whenever a coordinate system assigns a delayed path near gravity. It is not exceeded when a galaxy's cosmological distance grows faster than c. And it does not create a valid perspective in which a photon sees the universe frozen. It is the finite invariant that tells spacetime how to separate cause from elsewhere. Saying that c tells spacetime how to separate events may sound as though the constant issues instructions. Nature does not consult an equation before a flash moves. The equation expresses the pattern. Massless fields propagate along null directions. Massive bodies follow time-like paths. Space-like separated events lack direct causal connection. Lorentz transformations preserve the division. C labels the boundary. The boundary has practical consequences every moment. Sunlight reaching Earth is delayed. Radio signals guide navigation through measured travel times. Financial and communication networks depend on clock synchronization. Accelerators design magnetic fields around relativistic momentum. Medical imaging relies on electromagnetic interactions. Nuclear energy follows mass energy equivalence. Astronomy observes a layered past. Gravitational wave detectors compare light paths to measure moving spacetime. The number enters daily technology not because devices travel near C, but because precision makes tiny relativistic effects visible. A clock error becomes a position error. A frequency shift becomes a velocity measurement. A phase shift becomes a length measurement. A delayed pulse becomes a map. The constant also places permanent limits around ambition. No message can reach Mars instantly. No telescope sees a distant galaxy's present. No known engine carries a massive craft across the light cone boundary onto a space-like path. No civilization can coordinate a galaxy without delay. These limits are not evidence that exploration is meaningless. They give exploration its temporal shape. A probe to another star becomes a message to the future. A photograph from deep space becomes a record of a world already changed. A human traveler at relativistic speed could return to an age beyond everyone once known. The universe remains traversable in principle along time-like paths, but not synchronously possessed. Distance has consequences. This may be one of the most important things C creates. If influence were instantaneous, every region could be connected at once. There would be no causal horizon and no finite propagation history. With a finite invariant speed, the universe contains local presence, delayed knowledge, and irreversible journeys. Events happen beyond awareness and send information outward. Light cones spread through space-time like opening possibilities. Where two cones overlap, exchange becomes possible. Where they do not, no action here has reached there yet. Every conversation, collision, chemical reaction, and observation fits inside that structure. The scale is usually too small to notice. Nerve signals are slow compared with C. Sound is slower. Human transport is slower. The causal cone appears almost infinitely wide around daily life. Across astronomical distance, it narrows into destiny. The sun cannot know what happens on Earth now in any instantaneous sense. A signal must travel outward. The nearest stars lie years beyond a reply. The center of the galaxy lies tens of thousands of years away in light travel time. Causal connection is not the same as coexistence. A star and Earth can exist within one universe while being separated by years of information. This is why the night sky feels still even though it is filled with change. The changes arrive on different schedules. Some stars visible tonight no longer exist in their observed form. Some explosions have occurred whose light has not reached us. Some planets may contain life whose first detectable signal has not begun the crossing. The darkness between lights is also waiting time. The exact SI value of C can then feel almost intimate. That familiar number is exact because meters are now defined through it. The decimal belongs to our measurement system. The invariant structure belongs to nature. Say the number in kilometers, and it becomes about 300,000 per second. Say it in light seconds per second, and it becomes 1. Neither changes the causal cone. The real content is found in experiments. A light clock moves and accumulates less time relative to another path. Muons survive to the ground. Satellite clocks require relativistic correction. Interferometers fail to find an ether wind. Gravitational waves and gamma rays cross intergalactic distances almost together. Particle beams absorb enormous energy while remaining below the boundary. The theory survives because reality keeps performing it. There may still be deeper layers. Quantum gravity may change how space-time is understood at the smallest scales. Lorentz symmetry may emerge from a more fundamental structure rather than exist at the beginning of explanation. The constants of nature may be related by a theory not yet discovered. Experiments continue to search for dispersion in vacuum, violations of invariance, extra dimensions, and new particles. A future discovery could transform the meaning of C again, just as Maxwell and Einstein transformed it before. But any replacement must explain why existing relativity works so precisely across laboratories, satellites, particle accelerators, binary stars, black holes, and cosmology. New physics does not erase successful old physics. It contains it as an approximation in the domain where it has been tested. For now, C remains one of the strongest organizing principles known. It connects what can happen with what can be known. It gives massless radiation its path. It turns motion into time dilation. It makes mass a form of energy. It lets gravity carry waves. It gives the universe horizons. And it defines the ruler used to state its own familiar value. A pulse of light crosses an ordinary bedroom in a few billionths of a second. During that crossing, no eye can follow it and no thought can respond. The room seems to illuminate all at once. Yet the delay is real. The same finite delay, extended across larger distances, becomes 8 minutes from the sun, years from the nearest stars, millennia across part of the galaxy, and billions of years from the earliest galaxies. One rule spans the room and the observable universe. The light reaching the walls does not merely move very fast. It traces the edge of what can influence what. The darkness beyond the window is filled with older light still traveling, future light not yet arrived, and regions whose signals may never come. Space and time are not a stage waiting behind those journeys. They are part of the same structure the journeys reveal. That is why the speed of light is not what it first appears to be. It is a speed. It is a conversion. It is a symmetry. It is a horizon. It is the shape of causality written as a number. There is one final way to see the constant. Imagine two events separated in space and time. One is the release of a signal. The other is a possible response. Before any observer chooses coordinates, before anyone decides which clock is at rest, space-time already determines whether a causal path can connect them. If the second event lies inside the future light cone, a slower-than-light traveler or signal may reach it. If it lies on the cone, only something massless can follow the boundary. If it lies outside, no known influence from the first event can arrive in time. The distinction survives every change of inertial frame. An observer may say the separation is mostly time. Another may say it contains more distance. They may disagree about which distant events are simultaneous. They do not disagree about whether cause can reach effect. This is the quiet authority of C. It does not choose one observer's measurements as correct and discard the others. It preserves the structure beneath them. The number therefore appears wherever physics asks how one event relates to another. It appears in the equations of fields because disturbances propagate. It appears in mechanics because energy and momentum must transform consistently. It appears in gravity because geometry carries change. It appears in cosmology because horizons separate visible history from inaccessible regions. Light gave the constant its name because light made the boundary visible. A flash crosses a laboratory. A radio pulse reaches a satellite. A gravitational wave passes an interferometer while a gamma-ray burst follows. Ancient microwave photons arrive from the young universe. Each messenger traces the same causal architecture. The speed of light is fast enough to hide inside ordinary experience and slow enough to preserve the age of the stars. It makes a room feel immediate and the galaxy feel vast. It allows the universe to be connected without allowing it to be simultaneous. And every time a beam enters a detector, it completes one permitted path through that structure, carrying news from an event that could finally reach another. Good night.